Welcome to Connecting the Dots, the channel where we follow the breadcrumbs and try to predict where disruptions will take us. Tesla's Model 2 is a bold bet on untested technologies. It is a completely new car, which uses completely new innovative technologies. It is built on a completely new platform and will be produced on a completely new production line. And the line isn't just new, it is built around the completely new unboxed production process. If this seems a bit risky, good thing that they tone things down a bit by hiring a completely new workforce to make the car. And to be on the safe side, this workforce consists of humanoid robots, which take completely new to a completely new level. Pushing the risk matrix to its limits with so many levels of innovation is a recipe for either runaway success or epic disaster. So which will it be? Join me on this journey as we dive into the engineering behind Model 2 and its production and try to assess whether it will be a story of triumph or a cautionary tale of pushing the boundaries too far. Patrons make these videos possible, so a huge shout out to my latest patrons, John F.E. and Gary M. Your support is invaluable, so thanks guys. And to all my patrons, you guys rock. And now buckle up and get ready, because Model 2 will disrupt the entire automobile market. And one thing I promise you is that it won't be boring. Before diving into engineering, let's quickly review the highlights from the previous video. If you've missed it, don't worry. You can watch it later, there's no need to keep them in sequence. The previous video showed that attempting to accelerate production, Tesla's new factory will focus on parallel processes, modularity, and a dry factory approach that reduces liquid usage. Here's what this means for Model 2. Expect to see an electrically assisted drive-by-wire system like that in Cybertruck, as well as electrically actuated brake-by-wire. The factory will produce Tesla's innovative 4680 dry battery electrode cells, and notably, it won't include a paint shop. Contrary to rumors, Tesla won't cast the entire car or its skateboard chassis in one go. Instead, the top hat, or upper chassis, could be crafted as a single piece of forged or die-cast composite materials. And with the wiring embedded in the upper body's plastic resin and only connectors left exposed, the upper body will function as a giant integrated circuit. And the composite upper chassis will enable Tesla to delete the paint shop and switch to plastic or composite body panels. Tesla's vision is to create an alien Dreadnought factory operating without humans slowing it down and spitting out cars at breakneck speeds. If you're wondering how fast, consider this.
Yesterday, when I was being interviewed by somebody, I mentioned that a normal car production line is about 60-second cycle. Tesla is doing a 40-second cycle in China. Well, I've been corrected. That is really a 34-second cycle for the body shop. Nobody can do that.
Automotive production lines normally produce a new car every 60 seconds or more, and Tesla has managed to reduce this to 34 seconds between cars. But even that's too slow. With no humans to slow down production, the new line should spit cars out much faster. A few seconds between cars seems impossible, but in fact it very much is. All you need is to fanatically remove unneeded processes and parts, and then treat every process as a potential bottleneck, and meticulously work to shave seconds off. The technologies we will now see are all intended to shave seconds off and help turn Elon Musk's vision of an alien Dreadnought factory into reality. Chapter 1. Motors. There are numerous types of innovative motor designs, with arguments going for and against Tesla using them. For example, they could use asynchronous induction motors or synchronous permanent magnet motors, and they could use compact axial flow motors or keep using radial flow. The possibilities are endless, so let's start collecting some breadcrumbs and see where they lead us. 1A. Permanent magnets. First, Tesla already told us that Model 2 should use permanent magnet motors without any rare earth elements. This should lower costs, enable scaling, and mostly reduce the company's dependence on China. All this sounds great, but since rare earth elements are required for creating power-dense magnets that can withstand the magnetic fields within an electric motor, nobody outside Tesla knows how they plan to achieve this. I did some research and made a video on this, and here's what I said.
Nobody outside of Tesla has an idea what exactly Tesla will do, but we can assign probabilities to the different options. So there's a high probability that Tesla will use ferrite magnets. It's also highly probable that they'll use a ferrite core with a different coating. There's even a small chance of an iron core with coating. It is possible that they will use nanocomposite magnets. It is somewhat possible that they'll use tetratitanite. Logic dictates that the probability of this is small. For wishful thinking alone, I'm not ruling out this option. and there's a very small chance that they're using iron nitride magnets developed with or without Niren.
If you want to learn more, there's a link in the description. Tetrataenite is an extraterrestrial element found in meteorites, and I showed in my video why there's a chance that Tesla found a way to produce it. Whether they did so or not, I think we can all agree that Tesla's technology is out of this world. 1B, Hairpin Stator. Sandy Monroe told us that he saw that Tesla is making hairpin motors. Motors are comprised of two primary components, a rotating part known as the rotor, and a stationary part called the stator. Unlike traditional motors that utilize round wire windings, hairpin motors employ copper windings shaped like hairpins. These U-shaped windings are then inserted into the stator slots, marking a significant departure from conventional motor design. Hairpin motors offer several advantages over traditional wound wire motors, such as higher efficiency, better heat dissipation, increased power density, and improved mechanical strength. Their main allure for Tesla, however, is that their production is much easier to automate. Hairpin motors are easier to assemble by industrial robots than traditional wound wire motors due to their simple and uniform design. Their U-shaped hairpin windings can be easily inserted into stator slots, making it easier for robots to manipulate and handle them. Additionally, the uniform shape and size of the hairpins improve assembly efficiency and accuracy. This results in faster production times and lower manufacturing costs, which makes hairpin motors an attractive option for electric vehicle manufacturers. That being said, hairpin motors are for losers because, as we will now see, Tesla has one-upped them. 1C, Tesla's patented stator. Elon is extremely forward-looking, and as this 2011 patent application shows, Tesla started tackling automation of stator production back when Tesla still produced the Roadster. Overall, Tesla has almost 200 patents regarding electric motors, 51 of which focus on the stator. Most of Tesla's stator patents deal with automation. Let's look at one such patent, which Tesla applied for in 2020. The stator Tesla designed represents a significant departure from conventional stator designs, is much easier to assemble, and has higher performance to boot. I won't bore you with comparisons to traditional stators, so let's compare it to hairpin stators. The main differences between Tesla's stator and hairpin stators are: 1. Tesla's patented stator uses regular round cross-section wires, which are much less expensive and easier to obtain than the square cross-section wires required for hairpin stators. 2. Tesla's stator features a unique radial arrangement of teeth around a central axis, which facilitates easier and more efficient winding of coils on the stator's inward portions. 3. Tesla's stator incorporates wedge members placed between the teeth to secure their position and possibly enhance the magnetic flux path, which contributes to the motor's efficiency and performance. 4. Their stator also allows for the external winding of coils, which simplifies manufacturing and reduces the need for complex tooling. While Tesla could decide to remain with their current designs, there are good reasons for them to start using the new stator. Ultimately, the new stator focuses on external winding accessibility and potentially simpler manufacturing, while hairpin motors prioritize efficiency and performance gains using specialized flat conductors. With Model 2's focus on lowering costs and increasing production speed, the new stator seems much better suited for the car. Chapter 2, Octovalve Seats. Model 2 seats could differ from traditional car seats in several important aspects. We'll soon show their connection to the Octovalve, or rather the DecaValve. But first, let's discuss Tesla's breakthroughs in seat construction. 2A, seat construction. The conventional process of fitting seat covers, or skins, over foam padding is a laborious bottleneck in car manufacturing.
Some of these are like, the guy goes in with a nut runner. It's like, oh, okay, that's really easy. Oh, as a guy takes like some leather and he's trying to stretch it over this frame. He's like this big, bulky guy. And that's like all he does for 8 hours every day. He's like, putting him in. I was like, you mean to tell me he can do that repeatedly, on his
at that speed,
40 seconds all the time. I was like, man, that's going to be exhausting.
Stretching the skin to fit over the foam is a physically demanding task that slows down production. Accelerating it, however, is almost impossible because doing so would raise employee fatigue, increase the risk of repetitive motion injuries and on-job accidents, lower quality, and increase the occurrence of rejects such as skins getting torn or wrongly fitted. Tesla's solution: enter Optimus. With advanced dexterity and precision, this humanoid robot could revolutionize seat assembly by increasing speed while enhancing efficiency and consistency. But Tesla might have an even more radical solution up its sleeve.
The best part is no part. The best process is no process. It weighs nothing, costs nothing, can't go wrong.
The best part is no part, so why not eliminate the need for separate seat skins altogether? Tesla's skin foam patent proposes an integrated skin and foam component, streamlining the seat production process. Tesla's skin foam patent proposes an integrated skin and foam component, streamlining the seat production process. Tesla suggests pressing skin material into a mold shaped like the seat. Then an interim layer can be optionally added, followed by the foam, and the parts are then molded together. The interim layer is made of conductive mesh material and can be used to provide seat heating as well as serve as a seat occupancy sensor. Another option suggests directly spraying the skin material onto the foam. While skin foam seats aren't a new idea, they are typically used in non-premium seating, such as construction vehicle seats or bicycle seats. However, these do not provide significant comfort and give a low-rent feeling, while Tesla's version supposedly provides plush-feeling vehicle seating. Since covers would no longer need to be sewn together and fitted over the cushioning, the patent has a clear potential for simplifying production, eliminating a crucial bottleneck, and reducing costs. Tesla has yet to start using this patent, but in the world of Model 2's alien Dreadnought factory, there's a good chance that they will. 2B, installing the seats. In Berlin and Texas-made Model Ys, front seats are pre-mounted on the battery pack. This simplifies assembly and provides much easier access than the usual method of inserting the seats through the door openings of an assembled car body. The question arises, why not apply this method to rear seats as well? The answer lies in the design constraints of the Model Y. The seat's position is above the rear gigacasting, so the rear seat is inserted through the door opening and installed the traditional way. Model 2's back seat will also be mounted above the rear gigacasting, but the car's unboxed construction offers a solution. Rear seats will be mounted onto the rear module before modules are integrated together, providing the same efficiency and access currently provided in front seat installation. 2C Octovalve Seats. Tesla's patented liquid-based thermal management system for seats is another testament to their embracing innovation. As previously mentioned, traditional car seats use foam layers, covered by a seat cover, or skin. Heated seats add heating elements like those of a toaster, just below the seat's skin, where they can warm the surface on which the occupant sits. Ventilated seats add perforations in the foam base and a fan buried under the foam to push air through these perforations. Unsurprisingly, Tesla's patented thermal management system for seats is different. Similar to the thermal management system of the battery pack, it is liquid-based. In a nutshell, Tesla sandwiches a new layer between the seat's foam and its skin. This layer includes ducts or pipes through which liquid can flow. If the liquid is hot, it provides heating, while cold liquid provides cooling. Since Tesla's Model 2's front seats will be directly mounted on the battery pack, this facilitates integrating the seat's heating and cooling system with the car's overall thermal management. The new system is more efficient than traditional methods, as hot and cold liquid are often available for free. That being said, without having detailed data regarding costs, assembly time, and energy savings, there is no way to know whether using it in Model 2 even makes sense. Since Berlin and Texas Model Ys also have their seats mounted on the battery pack, yet still use traditional heating, there's a good chance that the new system won't be used in Model 2. If it is, however, I would love to see Sandy's teardown of it. Something about the thought of seats attached to the car's central thermal management system and getting cooled or heated for almost free has my engineering brain tingling with excitement. And here's something for you to ponder. If Tesla does connect the new seats to the car's thermal management system, will their control valves sit locally on the battery or centrally as part of the Octovalve? And if it is central, does this mean we should expect a DecaValve or a DecaValve? I love engineering, which makes diving into Tesla's patents exhilarating for me. But let's be real, patents are written in a complex, unfriendly way. That's why to keep learning science and technology as part of my busy everyday life, I use Brilliant. Brilliant, the sponsor of this video, offers fun, interactive lessons across computer science, data science, and math. They have thousands of lessons ranging from basics to advanced, and they're always adding new content. To learn new skills, I usually complete courses from start to end. But for me, Brilliant is more than a way to learn new concepts. It's also a great way to sharpen my existing skills. I love hopping between different topics based on what catches my interest. I recently started a case study called Going Viral on X from their Level 2 Introduction to Probability course. The case study uses simulations where I can apply probability to find how posts go viral on X and identify which posts are real and which are probably bots. Next, I plan to tackle the Maximizing Electric Car Value case study from the Level 4 data analysis level, which uses correlation and regression to sift through EV data and uncover what truly adds value for buyers. This blend of interactive simulations with real-world scenarios makes learning effective and fun. To make learning part of your daily life, Brilliant is offering a 30-day free trial when using my link brilliant.org/ctdots. These 30 days are completely free, and the first 200 viewers who sign up for an annual subscription will get a 20% discount. The trial is a great way to sharpen your skills and learn new ones, so why wait? Head on to brilliant.org/ctdots to start your learning journey today. And a huge shout out to Brilliant for sponsoring this video. Chapter 3, Wiring. As I anticipated, Tesla has introduced its innovative wiring hub, featuring 48 volts and Ethernet messaging. You probably know it provides significant weight and cost reductions, but did you know it is also vital for achieving alien Dreadnought production? In traditional car designs, each device, such as indicator lights, headlights, window motors, and door actuators, is directly connected to its control source, resulting in complex and bulky wiring harnesses. These harnesses, composed of numerous wires bundled together, are threaded throughout the car's chassis to connect each component. This makes the wiring system cumbersome, heavy, and expensive due to the extensive length of wires required. Tesla's solution is a game changer, with a shared wiring hub acting as a centralized power and command distributor for the entire car. Devices around the car connect to this hub locally using short wires and only respond to commands meant for them. This drastically cuts down on unnecessary wiring. The shift to 48 volts significantly reduces wiring thickness, achieving remarkable weight and cost savings, especially for remote actuation systems like steer-by-wire. A typical vehicle may contain up to 3 miles of wiring, weighing up to 100 pounds. In contrast, Tesla's Model 3 boasts just 1.1 miles of wiring at 42 pounds, and the new wiring hub goes much further. As a ballpark figure, I expect the new hub to reduce wiring by over 90% compared to conventional vehicles, equating to substantial savings in both weight and material costs. With copper prices at $4.5 per kilogram, this could translate into a saving as high as $180 per car in copper alone, not to mention requiring fewer batteries due to the lower weight. The savings are huge and deserve to get positive headlines, but there's more to it than just savings, because the new wiring paradigm is a key player in Tesla's push towards automation and achieving an alien Dreadnought factory. Traditional wiring harnesses require manual, labor-intensive assembly. In contrast, Tesla's streamlined wiring loop promises faster and more efficient production. And installing the wiring system into a car is less labor-intensive than traditional harnesses, which also enhances production efficiency. But most importantly, traditional wiring harnesses disrupt modularity because the car's body needs to be assembled before the wiring is threaded through it. Tesla's system, however, enables building and testing each module separately. Once built, modules can be tested by simply plugging their connectors into factory equipment, which emulates the rest of the car and automatically tests the module. This new wiring system also offers unparalleled agility. Changes in component design or placement no longer necessitate a complete overhaul of the wiring harness. For example, adapting a car's window controls for left-hand or right-hand drive becomes a matter of changing the switch assemblies so that the driver's door has 4 window controls and the passenger's door only 1, and that's that. The switches will automatically know which window to control, and with no need to change any harnesses, things don't come easier than that. Tesla's wiring hub brings automotive wiring to the digital age, but the best wires are no wires, so will Tesla go there? Wireless communications have made huge progress, with protocols and components now robust enough to handle interference and interruptions in automotive environments. In my previous video, I predicted that Tesla would start using wireless communications between some components. However, since gigabit communication speeds are now available a short wire connection away, the only place where using wireless still makes some sense is the battery pack. The reason for this is that battery packs involve monitoring hundreds of cells, necessitating a reliable data exchange with the battery control module. A wireless solution could streamline this process, offering individual cell control while minimizing internal wiring. Having said that, Without doing actual calculations, the benefits are unclear. Chapter 4. Connecting the parts. As explained in the previous video, in Model 2's unboxed production method, the car is divided to several modules, such as front, rear, center, and top. Each module is separately assembled and tested, and the modules are joined together to create an integrated body as late in the process as possible. So let's focus on this joining part and speculate on how Tesla will connect the modules together. Elon said several times that parts should fit together like Legos, and this is a great example. Imagine that while building something of Lego, you'd have to attach the bricks together with bolts or glue. That's not much of a game, and a whole lot of unnecessary work. Instead, you just bring the bricks together and they hold. The best process is no process, and the fastest way to connect parts is to have them automatically connect to each other when they are brought together without requiring any additional processes. For this reason, I see Model 2's production using snap-fit type connectors more extensively than ever before. As mentioned in the previous video, each of the car's modules will have clearly defined mechanical, electrical, and possibly also hydraulic interfaces to which the other modules connect. Let's imagine the process of marrying the upper body with an already assembled skateboard. As the top hat is lowered towards the skateboard, location pins ensure that both parts remain at the correct position. Then, plugs from one part enter sockets in the other, establishing all required interfaces. And finally, something clamps and keeps all parts together. Nothing more to attach and no welding, gluing, or fastening required. As Graham Brown, 42, commented on the previous video, this is already done in factory-built housing systems such as Huff House, and is definitely doable in Model 2 production. Unlike houses, however, cars undergo a whole lot of vibrations, jolts, forces, and moments, which over time loosen connections. This lowers rigidity, introduces squeaks and rattles, and ultimately causes failure, so I do expect Tesla to continue using conventional methods such as welding, gluing, riveting, and bolting where these are required. That being said, I do expect snap-fit type connectors to be used like never before. Chapter 5. Quenching. Tesla's deletion of parts and processes reaches all aspects of production, even the most basic processes such as producing extrusions. Aluminum extrusions are shaped by forcing heated aluminum through a die. For example, forcing aluminum through a square hole will result in square profile rods. Following extrusion, the parts are cooled using air or a process called quick quenching, which involves soaking the parts in a tank full of soft water or oil. While quenching is quicker, it can damage the material's properties. Quenching has 3 stages: vapor, nucleate boiling, and convection. In the vapor stage, when the extremely hot extrusion initially contacts the quenching liquid, the liquid in direct contact with the metal evaporates into gas. You know how when droplets of water hit a hot frying pan, they start dancing on it and it takes forever for them to boil? This is known as the Leidenfrost phenomenon. When the droplet hits the pan, the water in direct contact with the hot pan immediately evaporates. This forms a layer of vapor on which the rest of the droplet hovers, which leads to the dancing droplet movement. The vapor layer effectively shields the droplet from touching the pan, which slows heat transfer and lets the droplet last a long time before evaporating. Turning this upside down and focusing on the pan instead of the droplet, we can say that the vapor shielded the pan from touching the water, which slowed the pan's cooling. Going back to extrusions, the Leidenfrost phenomenon slows cooling, which can lead to soft spots in the material. In January 2023, Tesla was granted a patent for a process for quenching extruded metal parts using pulse-width modulated sprays of atomized liquid. What this mouthful means is that as the extrusions exit the die, they pass through varying pulses of quenching liquid spray. Tesla closely monitors the extrusion's temperature and controls spray parameters accordingly. By changing pulse duration and width and the size of the atomized droplets, Tesla is able to achieve rapid cooling while minimizing the Leidenfrost effect. Extrusions are created and immediately cooled in a single shot without wasting time for air cooling or a quenching tank, and while achieving superior results compared to open-loop cooling. As a manufacturing nerd, I find this remarkable. I wanted to suggest using this process to help quench gigacastings instead of using a quenching tank. But then I remembered, the best process is no process. And Tesla's gigacastings remarkably do not need any quenching. Chapter 6. Streamlining Production. As said in the intro, making cars just a few seconds apart requires each process to be optimized to the nth degree. Even the most trivial processes should be inspected and possibly changed. For example, let's give the optimizing treatment to the robotic arm which handles the gigacastings. Here's how it currently works. First, it enters the gigapress. There it grabs the casting and exits the gigapress holding it. The arm showcases the casting to cameras, and Tesla's digital self-management AI visually inspects the casting to verify its quality. The arm then moves the part into a redundancy removal station, where excess material is trimmed off. Finally, it takes the casting out and places it for transit to the next station. This process is highly efficient. A single arm handles the entire process from start to end, with some time to spare. It's clear that Tesla invested a lot of thought and possibly trial and error into optimizing this. So why do I even dare suggest that this should be optimized? The reason is that optimization is done for a working point, and what's highly optimized for Model Y production doesn't cut it for Model 2's alien Dreadnought production. Three things are wrong here. First, the robotic arm's multitasking could throttle production. This currently isn't a problem, and there's even some time to spare. But Tesla is working on improved gigapress cooling, which will enable the gigapress to operate much faster. And once this happens, the arm's current setup will find it hard to handle the pace. A more streamlined line could use dedicated arms for each step. With each arm handling a single action, cycle time can be greatly reduced. Second, Tesla should find a way to do away with the trimming. And third, the arm's back-and-forth motions lack the fluidity and efficiency of unidirectional or continuous processes. It's like comparing internal combustion engines where the pistons go back and forth to the smooth operation of rotary Wankel engines. Similarly, the current arm's movement is starkly different from Tesla's 4680 battery line's seamless flow. If possible for alien Dreadnought production, I would consider unidirectional movements, where, for example, the arm enters the gigapress from one side, grabs the casting, and exits the press from the other side. This should not only save energy, but also enable operation in much faster speeds. This was just a random example, but Model 2 production requires treating each and every process as a bottleneck and putting effort into deleting it or cutting its cycle time. Not everything will be changed right from the start, but if Tesla wants to achieve the highest production speeds possible, then gradually almost everything will have to change. Chapter 7, Cranking the Volume to 11. The main bottleneck in production is having to work at human speeds. Factories today work at the same pace as they did at the time of Henry Ford because although machines evolved significantly, humans remained very much the same. With Optimus robots replacing line workers, this major bottleneck will be reduced, but how much will this save if Optimus works slower than humans? Whenever Tesla releases a new Optimus demo with examples such as Optimus walking, handling eggs, or folding a shirt, some viewers conclude that the robot is much slower than humans, and it will take many years for it to work faster. This is far from true. Consider this graph by Tim Urban from Wait But Why, showing exponential growth. When people see robots doing monkey tricks, such as slowly handling eggs or folding shirts when operated by humans, they often dismiss it as having a long way to go. But with progress being exponential, monkey tricks only mean that very soon the robots will be as fast as humans, and a blink of an eye later, they'll be much faster. Tesla is building a streamlined production system with parts and processes deleted, bottlenecks removed, and production optimized, and they will operate it with rapidly advancing humanoid robots. Crank up production speed to 11, and the alien Dreadnought is about to arrive. Chapter 11. Will they fail? Okay, I'm just kidding with the numbering of this chapter, because unlike the Model 3 ramp, there is no risk of Tesla going to Chapter 11 even if production hell arrives and persists. But if Tesla wants to make 20 million cars, they need Model 2 to ramp. So will they make it or will they fail? We started the video saying how Model 2 is a bold bet on untested technologies. It is a completely new car, which uses completely new innovative technologies. It is built on a completely new platform and will be produced on a completely new production line. And the line isn't just new, it is built around the completely new unboxed production process. If this seems a bit risky, good thing that they tone things down a bit by hiring a completely new workforce to make the car. And to be on the safe side, this workforce consists of humanoid robots, which take completely new to a completely new level. We then saw how completely bonkers some of these new technologies are. And there's a lot I left out. For example, Tesla has a patent for welding steel parts to aluminum extrusions. This isn't crazy. They just use a nifty trick, and it is even possible that they will use it with Model 2. And while many of the technologies that I showed won't be used, several others which I haven't will be used instead. Pushing the risk matrix to its limits with so many levels of innovation is a recipe for either runaway success or epic disaster. So which will it be? On the one hand, it's enough for a single technology to fail, for Tesla to have production hell all over again. But on the other, Tesla of 2018 isn't the Tesla of today. Back then they were new to production, but now they are the best. Back then they were cash strained, but now they have cash flow to spare. And back then they battled an old and constrictive factory, while now they are agile and have room to expand. So will they succeed or will they fail? Taking a line from Warren Redlick, I don't have smarter than Elon syndrome, nor am I smarter than Drew, Lars, or Tom Zhu. I'm a kick-ass engineer, but I have far less data than they have on where each technology stands and what the alternatives are. To mitigate risks, there are many things they can start without and then gradually add, and based on their track record, I trust them to safely steer the ship. So yes, they will succeed, but it won't be easy. Here's what I think. Unless it happens in the next few months, Tesla will start production with very few humans involved. At first, things will go slow and ramping will be hard. Again and again, Tesla will solve problems only to face new ones. We will constantly discuss how production is behind schedule and just doesn't seem to pick up. But without us noticing, progress will be exponential. And just like with 4680s, once we are certain that production is too far behind, Drew will announce that, in fact, we are back on schedule. And then production will reach an inflection point and numbers will shoot to the sky, ramping much faster than with previous production lines. A funny thing with alien dreadnoughts is that once everything falls together, ramping can go like a bat out of hell. So yes, both Optimus and Model 2 production will succeed. Not financial advice, but I am certain enough to bet my entire worth on that. If it were any other company taking these risks, I'd be selling every share that I own, but these Tesla guys, they truly are pros. That's what I think. How about you? When do you expect Tesla to start making Model 2? Will it be built by Optimus, or will Tesla use humans? And will it ramp straight to Mars or crash to the ground? Let me know your thoughts in the comments below. If you like this video, please like and subscribe. Also consider supporting me on patreon.com/connectingodots because without patrons, this channel would not be possible. Your support really helps me make these deep dive videos. And you'll also get ad-free early access as well as exclusive patron-only content. Don't forget to check out Brilliant, the sponsor of this video, at brilliant.org/ctdots and get 30 days of free access. Come follow me on X, where I am connecting O-Dots. And until next time, I am connecting the dots, and you are amazing.